So hey guys, welcome back to my channel. Hope you are doing extremely well, and this is your very own mask code this side. So we are going to continue the Heaps playlist, and we are going to discuss the question kth smallest element. The problem is actually very simple. The problem says that you have been given an input array. This array is 7, 10, 4, 3, 20, and 15, and you have been given a k. You have been given a k as your input. It is also an integer. Suppose your k is given to you as 3, and now in the previous video we have to return the kth largest element, but now we have to return the kth smallest element. So how we are going to think about the problem? So kth smallest element, what does it mean by that? So if k equals to 1, that is first smallest number, that is the minimum element, right? In that case, what is the minimum element here? So you see 3 is the minimum element, right? So return 3. For k equals to true, what is the minimum element afterwards, right? That is, if you skip 3, then what is the minimum element in the remaining array? So you can say 4, you will return 4. For k equals to 3, you will have to skip 3 as well as 4. That means 7. For k equals to 4, you have to skip 3, 4 and 7. That means 10 will be your minimum, right? So how we are going to return it? We have the array in hand, we have our k in hand. So the brute force approach is actually very evident from here. Brute force approach says that sort the array. Sort the array. After sorting the array, it will look something like this. Minimum, next minimum, that is 4, then 7, 10, 15, 20. Am I right? Now I have to return the kth smallest. Now try to think, for k equals to 1, we were returning 3. Indexes mark कर लेते हैं 0, 1, 2, 3, 4 and 5. For k equals to 1, we were returning index 0, right? For k equals to 2, we were returning 4, which is index 1. For k equals to 3, we were returning 7, which is index 2. So you can see there is an analogy. For 1, we are returning index 0. For 2, we are returning index 1. For 3, we are returning index 2. So the second step is, this is the first step to sort. And the second step is return k minus 1th index, right, in the sorted array. That is simple, right? That is simple. That is pretty evident, right? Simple analogies. Now, what is the time complexity here? So to sort, you require time complexity of n log n, which is your time complexity. And what is the space complexity? So it is O of 1. Why O of 1? Because we are not using any extra space. We are just sorting the array in itself, right? That is in place. Now, this is the brute force. Obviously, interviewer will like you to start from here, but towards the end, he wants the optimized approach. He wants the optimized approach, right? So let me write down the array first. Our array was 7, 10, 4, 3, 20, 15. 7, 10, 4, 3, 20, 15. Suppose we are going for k equals to 3. That is, our answer is gonna be 7. Our answer is gonna be 7. Obviously, this is a heap lecture, so first thought in your mind is that I will be using a heap. But how? We're going to think about it intuitively, right? Heap. Now, I have got k equals to 3. I have got k equals to 3. My mind says that if I'm able to store some elements in a data structure, looking something like this, that suppose the size of this data structure is k, the size of this data structure is k, and last element or the first element, anyone you want, is 7, and the remaining elements are smaller than 7. Remaining elements are smaller than 7. So if for k equals to 3, 7, two positions are left, 1 and 2. What are the smaller elements? 4, 3. Obviously they are going to be sorted in sorted order, right? Then 7 can give me the correct answer. So first thing, we got sorted order. Second thing, we got 7 on extreme end, right? And smaller element. Why not larger elements? Because larger is not required, right? We require the smallest element. So left side k minus 1 element should be present, smaller element should be present. All these properties leave me to a max heap. How max heap? Because I require 7, and 7 is the largest among these k elements. That is why I was able to configure about a max heap. So my algorithm is actually very simple. I will be making a priority queue, that is a max heap, right? And I will start inserting elements into it. That is, first I will insert 7 into it, then I will insert 10 into it. 10 will obviously come at top. Then I will insert 4 into it, so 4 will come below 7. Then I will insert 3. Now after inserting 3, I will see that I required a k equals to 3 element, right? And 10 10 is already present at k equals to 4. If I insert any element, where are the perfect positions it can be? It can come here, it can come here, it can come here, it can come here, it can come here. That is for 10, it can come above or below. Wherever it comes, the position for 10 is gonna be greater than equals to 4, right? The position for 10 in the sorted order is gonna be greater than equals to 4. So 10 can never be the answer. And if it can never be the answer, remove it, pop it out. After coming to, it was not 10, it was 20 by the way. Sorry for my mistake. After pushing 10, after popping out 20, we pushing 15. 15 also comes here and it also positioned present at k equals to 4. Pop it out. Right? After popping it out, you can see that you have a priority queue remaining of k equals to 3 and the top element 7 is your answer. So what is that algorithm? So I going from 0 up till n minus 1, pq dot push the element. And now if the size of PQ, that is PQ dot size, exceeds K, exceeds, not equals to, exceeds K, then PQ dot pop, because the top element can never be the answer. At last, when the loop finishes, when this loop finishes, return PQ dot top. This is your answer, right? So what is the time complexity being used, guys? So we are going for O of n operations, and for each operation we are actually inserting. Now the maximum size of the queue is at any time is O of k, right? So we are going for O of n log k in terms of time complexity, and we are storing k elements at any point. So O of k as a space complexity, right? Okay, so this is actually very easy. If you do not get the intuition, please try to watch the kth largest element. I have gone in detail, right? It is just an extension of kth largest element. This video is just an extension, right? Okay, so let us move towards the code now. It is fairly straightforward. Here is the coding section, guys, and let us just start writing the code. But before it, please subscribe my channel because it really motivates me, and please like the video if you are able to get the concepts clearly, right? Now simply priority queue, because I want a max heap, so I will be just declaring int pq. Now for int I going from L up till R I plus plus, what will I do? I will first push the element, so pq dot push arr of I. And now if pq dot size at any point is greater than k, remember we are removing only when it is greater than k, not for equals to, right? Then pq dot pop, because the top element can never be our answer. And now at last return pq dot top. As simple as that. Let us try to compile and run it. Hope it will work fine and will not give any error. Working fine for the sample test case. Let us try it for the submission as well. And it is running fine. So thank you for watching. Hope you liked it, and we'll meet in the next video. Till then, stay tuned, keep coding, and make sure to subscribe. Thank you. Have a nice day.